Okay, so we'll start with today's topic on simulation of DC motor using simulink. Okay, okay, what is a DC motor? A DC motor is a rotary electrical motor. It is an electromechanical system that converts a direct current, that is electrical energy, into a mechanical energy. So whatever I was need to, this is a inverse principle of a Faraday's law. I'm going to say, what do you know? The Faraday's law's application, direct application, is a generator. Okay, whenever there is a two magnetic coil is there, whenever a conductor is going to be placed in it, whenever the conductor is going to be displaced, then automatically a current will be produced. That is the basic principle of your generator. Okay, so here it's going to be a reverse of that, my Faraday's law. So what I'm going to do, the two magnetic poles is going to be kept in your pot, and in this between this two magnetic pole, I'll have a one conductor will be placed. Okay, so what is here reverses of the generator? Instead of generating the current, I was giving a current to the conductor. So what is happening? See here, I have a two poles, north and south poles. So these are the two stator poles. Okay, and these I going to call the rotor poles, rotary equipment. This is a conductor where I was supplying a electric voltage or a current is supplied to this thing. So what is happening? So whenever the electric supply passes through this conductor, what happens? This conductor is going to possess some magnetic field to it. Is it or not? Any material which is having a current, which is going to have a magnetic property also. A magnetic property will have a current property also. This is going to be said by the Lorentz. So this, according to this law, this conductor, whenever the passing through a current, a magnetic force will be applied. So whenever there is a magnetic force, what is happened? The magnetic force is north and north. What will happen? This is going to repel to each other. Whenever repel to each other, this is going to move to the other side. Again, the voltage was given to the south. What will happen? This will also repel. So on repelling on the other side, so what will happen? The magnetic force here, see this magnetic force in pulling down this conductor. So this in turn converting as a mechanical energy, that is a rotational energy. Okay, so this electrical energy, the whatever electrical energy was given to my conductor, with the help of a Faraday's law, inverse Faraday's law, I going to produce the mechanical action. Okay, this is going to be just a reverse principle of my generator. Okay, a coil of wire with this running through the generators. So why I'm adding a coil of wires? So I see, as you able to understand the principle right now. So I was adding a coil of wire with the conductors. Why I'm adding a coil of wire with your conductor? Because whenever the coil is made up, what is the thing is the magnetic flux will be more. That is the magnetic field per area, unit area will be more when compared to your linear component. When wire is stretched in a linear, when current is flowing, the a magnetic flux, that is a imaginary magnetic area will be there. You see, one magnet is there. Whenever a magnet is there, two magnets or another magnet is attracted, or the ion was attracted because of the your magnetic field is there. Okay, magnetic field is there. Okay, so how far if I was take this two magnet for a further distance, what is happening? That the magnet will be distorted. So that is called a magnetic flux, the field, magnetic field. Okay, magnetic field. That density I'm going to call it as a magnetic flux. Okay, so to improve the magnetic density, so in order to have a conductor in a straight, I was having a wounded coil. So what is happening? The top and bottom, the coil is wounded. What happened? In the top surface, a magnetic surface coil will magnetic force will be applied, and the bottom surface, the coil is there. Bottom surface will also have the if I was wounding this coil here, what will happen? Top and bottom will have the magnetic flux. So in the middle of the your coil will have a high density of magnetic field. So I'm going to have a high magnetic flux. So if I'm going to have a high magnetic flux, I can able to produce a more amount of force. Okay, so this going to give me the RPM can be increased. So with the smaller amount of your current, so I can be able to give a larger amount of force. So only I will be most of your motors, if you're going to say, the coils will be wounded. Even a solenoids, everything coils are wounded because it's going to create a magnetic flux a lot. Okay, so this this is the architecture of or the simple parts of your DC motor. These is the housing cases, and this is having your stator and rotor windings. So this was coupled with a shaft, and the shaft was having a brushes. Okay, to the commutators are producing, the conductors are producing a magnetic flux. This mechanical actuation, I need to connect it to a brushes. Okay, so if there is a slippage will be there now. If the, so see this conductor is moving on, and I come giving a supply to a constant end. So what will happen? Your battery will also move to other side. To avoid it, I will have one brush. So the brush will also move along to this slippage. So now you understood that about the concept of DC motor. Okay, the direction and the magnitude of the magnetic field produced by the coil can be changed with the direction and magnitude of the current flowing through it. So what it says, if I want to rotate in the clockwise, I should connect by a positive and negative. If I need to rotate in the anti-clockwise, I'm going to change the polarity, so I can give it in the opposite direction of your motor rotation. Okay, so this is a basic principle of my your DC motor. So now we so far I already said MATLAB is a mathematical modeling. So I need to convert my DC motor into a mathematical modeling. Okay, so I want to convert this DC motor as a mathematical modeling. So, every object in real time can be converted as a mathematical modeling. So one does example is your DC motor. I can show you your, okay, DC motor I going to show. See, this is your circuit diagram for my DC motor. So this circuit diagram is called as armature circuit. So this windings are called as armature windings. So we're going to call it these north and south are called stator windings, and your windings rotated to your rotor are going to call it armature windings. See the same thing. North and south are my stator poles, and I will have a in between a rotor poles are attached. Whenever the magnet is current supply was given positive and negative to the slippage to the pressures, what will happen? This going to be rotated. Okay, so on base of this, a circuit model was done. So I'm going to give it the DC supply plus and minus. So this is going to be my motor. Okay, so why there is a two other components added in my electrical circuit, R and L. R is nothing but a resistance, L is nothing but inductance. Resistance is going to be nothing but I going to resist the supply voltage. So whatever voltage was coming, there will be some resistance will be offered by the circuit. Okay, so see if the windings are there, so naturally the property of the windings are made of material. Okay, it's made of aluminum, or it's made of some alloy material. So what is happening? Naturally it will have a friction, or you can say some opposition force will be affected by the material of the winding. So it is going to give you some resistance to the what. If I'm going to give 5 volt, surely it will not be converted into 5 volt. It will be reduced to some certain voltage because of the resistance offered by the wires. So that is called resistance. L is nothing but my inductance. Inductance is my storage of my current. Okay, storage of my current. Okay, inductor is nothing but. So whenever I passing the current, it is resisting in the mean of storage of my current. Okay. Okay, now the motor is and this motor was attached to a shaft. So this shaft we're going to look at up. Okay, we'll discuss what is the shaft. So this is, you understood about the electrical connection. Simple motor is here. Motor is attached. Simple motor was attached with the voltage source. So and this voltage source is going to have two other components: resistance and inductance. So inductance, it will be there in the armature coil. So but I was cutting the circuit. Is it or not? Whenever I cutting a circuit, there will be a current will be current is cut off. Is it or not? See, the magnetic coil is here. I was rotating. So what happens? This was cutting the magnetic coil. So there will be some amount of your cutting of current will be. So this going to call this inductor. Okay. So the inductor is going to store the current. So a resistance in the form of storing the current. Okay, so current will be reduced. R is going to reduce my voltage. L is going to reduce my current. Okay, these are the your reducing factors, or the factors which are reducing in my physical parameters. Okay, so this it's my motor. Okay, now this motor is attached to a shaft. Okay, whenever I was giving a supply voltage, so what has happened? Motor will be started to rotate. Whenever the motor is rotated, I was already told it will be having a I'll be having the shaft is attached to it. So the shaft will also start to rotate. Shaft is nothing but a linear rod which is outside from my, you see, one rod is attached to outside. So whenever I was rotating, I should elevated thing, some elevator rod is there to rotate it. So this is my elevator rod is attached. So I can say example if you are fans, okay, you have a fan in your fan, you have a motor in my fan. So whenever rotating, the blades are rotated, is it or not? Blades are called as shaft here. Okay, so now what is the thing? Whenever the blades are rotated, so I'm going to have two things. So whenever fan is rotated, I'm going to say what are the things. So okay, I can say in a linear or a translation motion, when an object is moved from one part to another part, what are the necessity things I needed? First, I need to object to move from one part to another part. I need a force to move from one part to another part. Is it or not? So that force I'm going to call it here as a rotational force. Yeah, that is a linear force. Okay, it's in the rotation. It's a rotational force. I'm going to call it as a torque. Okay, and I'm going to have an angular when after gaining a certain force, the motor shaft is going to be rotated. So angular velocity is nothing but speed with the direction. Okay, it's going to angular velocity. So the angular velocity is said in the form of omega, and rotational force or a torque is said in the form of t. Okay, and b theta is nothing but my acceleration. Okay, so I'm going to talk about my theta dot is nothing but omega dot. Theta dot is nothing but omega dot. Okay, omega dot is nothing but my acceleration. Okay, angular acceleration. Okay, b is nothing but my damping force. Okay, we'll discuss about later. Now you understood about the torque and angular velocity. Okay, whenever shaft is rotating, so the rotational it is going to supposed to have with the rotational force. Shaft is needed will be attend some rotational force. So what is here? This voltage is given. The conductor is rotating, so that is rotating in the form of rotational force. Okay, and the angular velocity. So after rotational force, I'll be getting an angular. That angular velocity is the speed of the shaft. Okay, speed of my motor, I'm going to say is angular velocity. Okay, to in a simple term. Here, and one more term is called back EMF. What is the back EMF? That's called reverse voltage. So see here. So whenever this motor is rotating, so this rotating, what will happen? So here, this is also rotating shaft. This is rotating. What will happen? This is going to cut the magnetic coil. So the small amount of reverse voltage will be generated. So this is the principle of, see, to say it, now I was using inverse Faraday's law. Is it or not? To inverse Faraday's law, what is happening? This is making my conductor to move, conductor to rotating. So while rotating, so what I'm doing, I'm cutting this magnetic flux. So what is the Faraday's law say? Whenever a conductor is cutting a magnetic flux, a current will be produced. So because of this, a current, opposite current will also be produced. Simply say Newton's third law, for every action there is a equal and opposite reaction. So whenever I start to rotate it, there will be some opposite action. So because of the opposite action, I was producing this back EMF. Okay, produce a reverse voltage, that is going to call as a back EMF. So this back EMF is going to be calculated in my total voltage supply. If I'm going to rotate my DC motor in a faster manner, this back EMF will also be increased and it will reduce the speed of my motor. Okay, so for that, for this is the only purpose. So what is I can theoretically I can say, whenever a supply voltage is given, a DC motor can rotate. If I'm going to increase the amplitude of my voltage, DC motor will also going to be increased this amplitude. Is it? Sorry, speed will also be increases. But what is a really disadvantage of thing is in real time what is happening? Even though I was increasing my DC voltage, at one certain point of time, I cannot increase the speed of my DC motor. Is it not? That is I can say DC motor set my fan. Even though I was giving a more amount of voltage to my fan, the fan cannot able to rotate beyond to a certain amount of voltage or a current, certain amount of current is you cannot able to run because of this back EMF. The back EMF is created more or equal to my given voltage supply. So that will oppose my current to passes to my DC motor. So a steady state will be attained after is given a voltage of more voltage. I will be attain a steady state condition. Okay. So this meeting will end in another 5 minutes. Just open again in the same meeting.
Okay, sir.
Okay.
Okay, sir.
Okay, sir.
Okay. So can we go for the next topic? You understood about this
Yes, sir.
circuit?
Yes, sir.
Yes, sir.
Now that's electrical to mechanical conversion. So this where my components comes. So before going to the equation and derivation, I'm going to say about so x of t is nothing but the input to the circuit. Y of t is nothing but the output of the circuit. So what is the input of the circuit? What is the input we are giving to the circuit? We are giving the voltage. Is it or not? We are giving the voltage. See, plus and minus. So voltage is my current. We are giving the current to my battery is my input. Is it or not? I'm going to give the battery to my motor, and what is the output we are expecting? The speed, or I'm going to call it as the angular velocity. So I'm going to say omega. That is the angular force. I'm going to so whenever battery is given, I'm going to ultimately at last I need my fan should be rotated. Is it or not? If fan is rotated, automatically it is going to gain the speed. Okay, so I'm going to need a angular speed is my ultimate requirement. Omega is my ultimate requirement of my speed of my motor is my ultimate requirement, or the torque is my ultimate requirement of my output supply. Okay, angular force is going to be my ultimate need of my thing. Okay, whenever voltage is given, speed is there. If voltage of a battery, the battery is increase, the current will increase. Naturally, the speed of my DC motor will also increases. Okay, so that's where my input and output components are there. So x of t is nothing but my input terminal, y of t is nothing but called the output terminal. X of t is a Vs, Vs is my supply voltage, and y of t is omega. Omega is nothing but my angular velocity. Angular velocity is called simply going to call speed of my motor. Okay. Uh, okay. To in order to attain this relationship, so now I need a relationship between my input. So I know what is my input, what is my output. Now I need to derive the form. So what this input, what is my output is going to be. So you have a masala and you need a final recipe. Now I need to give the recipes in between. Is it or not? I have masala and final food is there. I know what are the ingredients to my food and what is my final outcome. But I need in between masalas and recipes to be done so that we're going to derive it as a mathematical format. Okay, before going for my we'll start from output voltage. Output thing, what I required ultimately my angular velocity of the load. So I need an angular velocity. That's the speed of my load. So the speed of the load is nothing. So to derive the speed of the load, we'll go need an angular force. Okay, when the angular force is given, then only I'll be supposed to have a angular velocity. So torque is nothing. I go to what is the torque? I already said it's a force. F is equal to ma. Okay, you know that Newton's law. Okay, F is equal to ma. So here mass. What is mass? It is a weight into the gravity. Supposed to, is it or not? Mass is nothing but weight. The weight of an object into the gravity. Okay, W into G will be my mass. Okay, weight was supposed to be in a gravity. So I'm going to say instead of here in angular, I don't have a gravity here. Here I have a moment of inertia. What is the moment of inertia? According to your Newton, what is the moment of inertia? Whenever a body started to rotate, it cannot able to stop unless otherwise any external forces acting. So that is creating some moment. Okay, on rotation, it is going to create some moment. So this instead of m, I'm going to add a moment of inertia, which is going to symbolically noted as IL, and A is nothing but my angular acceleration. So the angular force is equal to your moment of inertia into angular acceleration. It's a simple analogy of my F is equal to ma. Okay, F is equal to ma is in terms of rotational force. I'm going to say it is a IL into omega dot. Okay, angular acceleration. Okay, so this you understand. Okay, now this electrical analogous to torque. So now this torque is now this torque should be needed to be produced from my voltage. So Vs should supply to my things. So how this voltage is going to be done? So see here, Kd is a constant. So how this torque is derived directly from the current. How much amount of current is given, that much amount of force is derived. Okay, so torque is directly proportional to the current which is produced from the battery. Okay, is it or not? So if I'm going to give a 1 amp of current, I'm going to have a 10 RPM. If I'm going to give a 2 amp of current, I'll get 20 RPM. So if I'm going to have a 3 amp, 30 RPM. So it is proportional. Okay, your torque is proportional to the rate of current discharged by the battery. Okay, so I'm going to equate that. Okay, KD is a constant. Okay, constant is nothing but if any external factor is added, I'm going to add this KT. Okay, KT into I of T, which is equal to my mechanical mechanical component of moment of inertia into omega. So what is this? Current produced by the battery, which is equal to the torque produced in the shaft. Okay, so I was giving electrical analogous to the torque. So now I know the I of T is the main component to rotate my shaft. So how this I of T is generated with the help of Vs. So voltage, whichever the voltage is given. So this is whatever the voltage is given, I will be generating the your current. So how to find the current? I is equal to V is equal to IR. That's Ohm's law says V is equal to IR. So I is equal to V by R. So voltage in the circuit, I should calculate the voltage in the circuit and the resistance offered by the circuit is going to say in the I of T. So I know this V of Vs, is it or not? I know this Vs, which is I'm going to give it 5 volt. So next step, I need to know what are the components opposing to my Vs. So which is going to pull my Vs down. Okay. So I'm going to know. So what are the supplied voltage Vs? So what is there? Voltage drop in the resistor by the coil. Okay. So the coil is here. Is it or not? The coil is going to be offer some resistance. So that resistance I'm going to call R. So in terms of Vs, so I'm going to what is how much amount of voltage is dropped? B equal to I into R. So I'm going to write in the form of R into I of T. Okay, I into R. That's the way I of T into R. So why I'm putting I of T? It is a continuous. Okay, I of T is nothing but it's a continuous variable. I of T is nothing but so if the DC motor is running at 1 second, 2 seconds, 3 seconds, what is my current rate at that 1 second? So T's value is going to be start from 0 to infinity, the time period. Okay, so this I'm going to say it is a continuous system. So I'm going to say R into I of T, IR. Okay, plus so what is another resisting component in my circuit? I have an inductor. Okay, the inductor formula is L into di of d by dt. Okay, so you just go through the basic principle of inductor. Inductor is nothing but a storage of my current. Okay, the rate of change of my current. If in a wire there is no change in the current is there, so there will be zero amount of inductance value will be 0. There will be no change in my inductance. But if there is a change in current due to the voltage supply or something, immediately my inductance will also vary. So this change in current is going to give my inductance. Okay, so L into dA of d by dt is my inductance factors plus VB. What is this VB? What is this VB? Back EMF. The voltage produced by the back EMF. I'm going to call it as a VB. So these are the factors. It's going to reduce my VS. So that VS is nothing but supplied voltage. Let other students come and join. Okay. So what is VS? VS is the input supply voltage, and the input supply voltage should be equated to the drop of voltage in the complete circuit. So what is the drop of voltages are happen because of the resistance offered by the coil. Okay. So resistance is nothing but V is equal to IR. So I'm going to say write it in the form of R into I of T. Why I'm writing everywhere I of T is nothing but it's a continuous system. It's a continuous system. So what is the continuous system means? The DC motor is running for every moment of time period. If I'm going to calculate for a discrete means for a, say if I'm going to say 10 o'clock, what is my current? After 10:30, what is my current? 10:40, what is my current? That I'm going to call as a discrete. So where I put off I, R into I, I into R. Okay, but it is a continuous system. I will not measure by R by R seconds by seconds. It is a continuously, it is going to be monitored. So I'm going to say it is a I of T, something but a continuous system. I'm going to take the data. So next is my inductance. Inductance formula is L into dI of dt by dt. Why? What is dI of T by dt? It's a rate of change. I already said that. Okay, what is a wire inductance? Whenever current is carrying in a wire, whenever there is a rate of change, then only my inductance will be there. Otherwise, inductance will be 0. Okay, so change in the current, whenever change in current happens, inductance will be affect my complete circuit. Okay, and next is my VB. VB is nothing but the current or the voltage drop because of the back EMF. The voltage produced because of my back EMF. Okay, so all are going to give a share to my VS. Okay, so now we have gone to the electrical analogous. Now we'll have the mechanical analogous to the back EMF or reversal. So how this, so we have how this back EMF is produced. So I already said with the your shaft is rotated. Whenever the shaft is rotated, so what automatically happen? It is going to cut my magnetic field, which is created by my two stator poles. Okay, whenever this cuttings happen, the Faraday's law is applied. So there is a reverse voltages produced. That reverse voltage I'm going to call it a back EMF. So there is a relationship between my rotation of shaft with my back EMF. So I'm going to give the relationship between them. Okay. The angular velocity of the shaft increases, the back EMF will also increases. So to give a VB is equal to what is it? It's directly proportional to the your angular velocity. KB is nothing but a constant. KB is a constant value which is going to be given KB into omega. So KB VB is proportional to omega. Okay, VB is equal to KB into omega. So now I'm going to substitute the back EMF in the previous equation. So I know that what is a back EMF? VB is equal to KB into omega. So what is VS? So supply VS is equal to R into I of t plus L into dA of dt by plus KB into omega of t. This is the equation will be given. So so angular velocity given. What is angular acceleration? It's nothing but omega is nothing but my omega of d. Oh, sorry, this is dot should come here. The presentation. Omega dot is nothing but my angular acceleration. Yeah, it's nothing but acceleration is equal to what is acceleration is equal to dv by dt. Is it or not? So omega dot is equal to omega of t by dt. So and to find my acceleration, why I need acceleration? We have discussed in my torque. Torque is equal to kT into I of t, which is equal to my moment of inertia into d omega of t by dt. That's it is again dot will come here. There is a d omega dot of t by dt. Okay. Okay. Now, if we're going, so now I need it. So I need to find this omega of t. Okay. I need the value of omega of t. So how to find this omega of t? So I can derive from this equation kT into I of t is equal to IL into d omega of t dot. Okay, this is by dt, which is equal to. So what I going to keep d omega of t by dt. This is nothing but acceleration. Okay, d omega of t by dt is equal to kT by IL into I of t. So when I was integrating this d omega of t, what will I'll get? So what I'll get? Whenever I integrating d omega of t, I will get w omega of t. Is it or not? So I to find my omega t, I'm going to integrate my d omega of t by dt. So omega of t is equal to integral of kT by IL into I of t. So this is the equation derived from my torque. Okay, from the torque equation, I'm going to derive it here. You understood this step? Or you want me to repeat it? Can I repeat it?
Yes, sir.
Okay. You have you understood this step. Vs is equal to R into I of t plus L into dA of dt plus BVB. This is just get from this equation. So Vs is equal to, so the voltage in the circuit is equal to, so what happened? This voltage is at 5 volt. Whenever it's coming to the R, what will happen to this? R will reduce by 5 volt to some reduced voltage of 4 or 3. Okay, when it is passing through the inductor, again there will be a drop in the voltage whenever the rate of change of current is here. So again it will come here and it will going to give a 3 volt of current to my voltage, 3 volt of voltage to my motor. With the 3 volt of voltage, what will happen? My shaft is started to rotate. When the shaft is started to rotate, So it is again going to produce a negative voltage. So this 3 volt is keep on reducing to the on after a periodic time period. This 3 volt is going to keep on reduced to my 0 volt. Is it or not? So that is going to be say here. So Vs is equal to that's 5 volt is equal to R of I of t. R of I of t is nothing but my the voltage reduced in my resistance plus L into d of t d is nothing but voltage reduced at my inductor plus my voltage of my back EMF will be given here. Okay, so up to this you understood. So so back EMF is directly proportional to the how the back EMF produced. Whenever the speed is increases, my back EMF produced. So VB is proportional to the omega. So the speed is proportional to my back EMF. Okay, so now I'm going to substitute this back EMF in the previous equation KB into omega of t. Okay, now I know already the formula already from my torque formula. KT into torque is equal to KT into I of t. That is torque is directly proportional to the current. Okay, and this current is okay. This torque is also proportional to the moment of inertia into angular acceleration. That is F is equal to ma. So I'm going to equate both of things. KT into I of t is equal to IL into d omega of t by dt. That is acceleration is changed in the form of speed. Okay, A is going to return in the form of speed. That is F is equal to ma. I can write it as F is equal to m into dv by dt. Is it or not? So that is only I was written as IL into d omega of t by dt. So now I need to find my omega of t. Okay, so that is my ultimate requirement. So how to find my d omega of t? So whenever I going to integrate d omega of t by dt, I'll be getting the omega of t, which is equal to integral of kt by IL into I of t. For initial condition 0, so I of t will be also 0. So for initial condition it will be 0, and after the rate of t is increasing, your speed will also increases. Okay, now you understood how the omega of t is arrived. Okay, so now I need to, what is my ultimate requirement? So everywhere I was having a I of t, is it or not? I don't record Vs. I need I of t. I of t is the current produced. So I need to find the I of t. So how to find the I of t? So keeping your I of t in the one component, remaining to the other component. So what I'm going to do? So d of t by dt is equal to Vs minus R into I of t minus KB into omega of t by L. So how to find this omega of t? This omega of t I was finding here. Integral of kt by IL into I of t. Okay. So now integrating this di of t by dt, I will be getting the I of t. Okay. So now I found my current. So I got my, what is my current? So with the help of this current, I can find my omega. Without the help of this current, I cannot find my omega. Omega of t is required I of t. Is it or not? So I need I of t. So omega is my output and my Vs is my input. So now I found a relationship between my input to my output. Is it or not? So Vs is equal to R into I of t. What is I of t formula? Here it is there. It is going to substitute. So whenever I'm going to substitute all my values here, so I'll be getting the values of my omega t. So whenever substituting all this is omega of t value, so I'm going to find the relationship with my input and output component. So this is the mathematical modeling of my DC motor. So now I'm going to just write it in my MATLAB and solve it. Directly I'm going to write this equation and to solve it in my MATLAB. Or otherwise, in a simulink, what is the advantage of a simulink? It's a drag and drop modeling. Like my LabVIEW, I don't want to see in my MATLAB everything. If I want to integrate, I need to type my commands. So right, instead of typing commands, I'm going to give a physical modeling, or I'm going to say simulated modeling like my LabVIEW. It is a drag and drop method will be utilized to derive this modeling of this mathematical modeling of any component. Instead of writing as a mathematical equation in a MATLAB or your commands, I'm going to derive as a blocks or models in a simulink. So to start my simulink, I'm going to use two different methods. So before going to start, you understood about the mathematical modeling, right? Okay, can we go for your simulink?
Okay, sir.
Okay, to start my simulink, I can start my simulink in two ways. By typing simulink in my command window, so I can able to start my simulink, or I can find your simulink tab in my home window. Okay, in a home window, I can find my simulink tab. Either I was clicking the simulink, I can open my simulink panel, or I going to go for my simulink typing simulink command. Okay, blank model. After going for a king, I going to give a blank model, create my blank model. After creating a blank model, now the blank model is created. Now I need to take out my components. Is it or not? To take out my components, so I'm going to use a library browser. Library browser, which is going to have all my component model components are we can find it in the library browser, or I can also type it in the window. Also I can type whatever the components are required. I can directly in the window. Anyway, I'll show it in the practice session. Okay, so drag and drop the components. So I have all the components are available in my library. There are different hierarchies here. Commonly used block, continuous. So we are using continuous mode, discrete mode, dashboard, and logical and bit operations, lookup, math operations. Okay, more important is sinks and sources. Sink is nothing but which is going to be grounds, the grounding terminal, or which is going to be the terminal which is going to be given its output. Okay, it's going to be say its output. It's simply say sources are going to be say is a input supply. So sources are the voltages, DC voltage, AC voltages. Everything is coming under your sources. Sinks are my output. Sources are input, and sinks are called output components will be available in my things. Okay, and these are the components are required for my from my library for browser for this DC motor modeling. So I going to have a first the equation is going to have a BS. Is it on a BS is nothing but my voltage supply. BS is required, and I need a gain. Okay, this is going to be stepped input. Stepped input is nothing but if 5 volt is given, it will be having a 5 or a 0. Okay, it will have a stepped input, square wave input will be given, or the discrete type of event will be given. Okay, next is my gain component. Okay, next this gain is nothing but it's simply going to say product or multiplication. Okay, so this gain is nothing but whatever the gain from components constant is given in this. So whenever the input is coming, it is multiplied by the constant it is giving. Okay, if gain is given 1, so if I was giving input as Vs into 1 is equal to Vs is supply voltage. So 5 into 1 is equal to 5. If I going to give gain factor as a 2, 5 into 2 is nothing but 10. So gain is something but a multiplication factor with a constant. Okay, I don't have a multiplication, but multiplying two other components. Here it is a multiplying the constant with the input. Okay, whatever the input is coming, I going to multiply that input with a constant value. So I going to call it as a gain. Gaining the input is going to gaining the value, whatever the things, it is going to call as a amplifier. I'm going to say whatever value is coming, it is amplifying the value. Okay, if it is minus, it is going to de-amplify. If it is positive, it is going to increase the value. Okay, next is the integrator. It is shown as 1 by s. We're going to use the two other components, W of t and I of t. Okay, we have omega. W of t is nothing but omega of t and I of t. Here two integrators are used. So after all these things, I need to see through a window. I need to see the output as a window. So I'm going to use a scope. Scope is nothing but it is going to show you a graphical structure, or here I'm going to say show the graph of my output. Okay, so this is going to, so I have a two outputs. One is omega out and current output. Okay, and next is my add additional blocker. So what is here? Vx plus Vs is equal to I into R plus L into di by dt plus Vs. So I'm going to add 3 components. So I need a add, which is going to available in my math block. Other components can be available in the commonly used block. Your voltage supply will be available in the source block. Okay. So in add block, what is the thing is, naturally, so add block will be coming with 2 additions or 2 number of additions only. You can able to add only 2 other. If you want to add 3 other components, just double click the block and change that how many symbols, plus and plus and plus. So again, plus plus minus. So what it means, it can add a 2 component and subtract the value from this. So this math block can be used to go on to my properties. Okay, these are the blocks I'm going to use it in my browser. Okay, this is my simulink model. So I can directly go to the practical section and I'll come again for this thing. Okay. Okay, here is my thing is available. Can you able to see that simulink? Or I will increase the font size. Okay, simulink is here. So just type simulink and give enter, or you can see here the block is there in my top window. Go to simulink and give this. So I'll be having my model. So I was going to open my blank model. Okay, create a model. Can you able to see my simulink window?
Yes, sir.
So the command window, no, sir?
No, the simulink window.
No, sir.
No,
No, sir.
because I have doubt of that one. Okay, now you're able to see the simulink window.
Yes, sir.
Okay, fine. This is my simulink window. So I can either go in a 2 different way. Like I can go for library browser. So okay, now I'll show the library browser and later I'll use the thing, because I cannot able to switch over between again and again with the screen sharing, because now the library browser will not visible. Is it visible? I don't think it will be visible.
Which one, sir? It's showing model browser in the corner, sir.
Okay, now
Library browser, yes, sir.
okay, and so the library browser is there, is it or not? So from this library browser I can take my blocks, commonly used blocks. So I have a commonly, in a general, what are the blocks are used? It is going to be having integrator. You will be having my scopes, okay, and your product multiplication, addition, input, supply, constant. Everything was available in my commonly used blocks. Okay, and sources will be available in my sources. I have all my inputs. Okay, so it's a band limit, white noise, a chip signal. These are the noises I'm going to add it, clock, or I'm going to give a constant to my output input. So what I needed, VS is required, is it or not? So I'm going to go for my step input. So I even go for a step, select my step, drag and drop it here. Drag and drop it my model window. I hope model window will not visible to you. So I'll change it my. Okay, now you have seen my model window.
Yes, sir.
Okay, now this whenever dragging and dropping, your thing is visible. Okay. So now I add a stepped input. Is it or not? So now this stepped input is nothing but my VS. So I can change my name of my model as VS. This is my supply voltage. So I'm going to give it, okay. Before going to my supply, what is my final thing I needed? I need I of t. Okay, I need to find I of t is my final thing. Okay, so to find my I of t, So what I need, I need an integrator. So IFT is nothing but integrating my integrator. So type, just double click on the model window so I can able to get my annotate mode. So here I'm going to type integrator. Okay, I'm going to have my integrator. So label the integrator. What is the name of this integrator? I of T. Okay, so this integrator is done. So just a minute. Copy my number. Okay, these are my two equations. I need to put onto my thing. Can you able to see the equation? So I need to I of t to be derived. Is it or not? For deriving I of t, what is I needed? Integrating of di of dt. Okay, so I will be getting I of t. For this I of t, I needed to integrate Vx. Say Vs is my voltage supply minus R into I of t. Is it or not? R into I of t, I should go for that. So R is a gain. I going to add it. So add my gain factor. Gain is 1. Let us have replace the gain factor as R. Okay, and next component I need. So what is this? Okay, what is the input for my thing? So I need R into I of t. Gain is Z or not? So my input should be. Okay, so what is my output of this gain? R into the whatever the integrator I of t. So whatever the value comes, the I of t into R. That is my R into I of t. Okay, and I needed next what is there? Minus Ka into omega of t. Okay, what is that? Ka into omega of t is nothing but my Kb into omega of t is nothing but back EMF. Is it or not? So I need to have one more. I need to have a gain factor. What is the name of this? Kb. Okay. So what is the thing is Kb into omega of t. Omega of t I have not derived it, so I need a. So how to get the omega of t? Omega of t is equal to integral of kt by il into I of t. Is it or not? So I'm going to get a integral. Is it or not? So add one more integral. Okay. So what is the initial condition as 0? No problem with that. It will take a default as 0. So I'm going to take integrator of what is this? Omega of t. Okay, it's a integral of omega of t. So omega of t integral, what is my for the input for my omega of t integral? Kt into IL. So I add one more gain. So I'm just going to copy this and paste it and replace the value of thing is KT divided by IL. Okay, so I can add a simple, moment of inertia is also constant, is it or not? Moment of inertia will also not change. So I'm going to have a moment of inertia IL, okay, KT by IL. So what is a KT by IL? Which is going to be, so for multiply by I of t, is it or not? So I'm going to get an input from my KT by IL. So after KT by IL, so what is my output? I of t into KT by IL, which is going to be given to my input for my integral of omega of t, is it or not? Integral of d omega of t. So what is my output from this? I'll be getting a omega of t is my output, is it or not? So output is omega of t. So that I'm going to fetch it to my kb. So what is my output of here? Kb into omega of t, is it or not? So kb into omega of t is the thing, whatever I required. So I need, so what is this? So what is this? I need add all these components, is it or not? So I need a one adder. So whenever it's coming, it will have a plus and plus. So I can change what are components. When I add 3 plus, what is added? Three component can be added in my components. So now I'm going to add my 3 components. Okay, what are the components? First, my Vs is added. Okay, next, what is there? Vs minus R into I of t. Okay, either I can change it here itself minus, or I can change in the component there also, no problem. So now I'm going to minus R into I of t. Then I'm going to have a Ka into omega of t, is it or not? So Kb into omega of t. So this is my Kb into omega of t. So I'm going to add all my circuit to my adder circuit. Then what is happening? I should divide the total component by a L. So I add one more gain. One by L. Okay, it's the inductance 1 by L. So what is happening now? I'm going to give it to here, and this is going to be given to my 1 by S. Okay, so now I got the 2 different things. See, I can able to. So now this work is done. Now I need to see the waveform. Okay, how to see the waveform with the help of scope. COPE. Go to scope. So I need to check I of t. Okay. So I can say it is a I out or the RPM or the force. Okay. And I need to go for my omega out. Omega is nothing but my angular things. Where is omega of t? This is where my thing. Okay. So copy. So this is where my equation is followed. So you got it out. This simulink model is derived. Okay. Now I'm going to comment it out. Can you able to see the screen? So what is happening? Whenever the motor start to run, so initially I out, what is I of t is 0 and it start to gradually increase. Is it or not? This start to gradually increases as my motor is keep on running. Okay. So now I'm going to see my I out. Okay, you have next topic of simscape modeling. Okay, simscape for electromechanical. Electromechanical again, it's a it's going to involve electrical and mechanical mechatronics. Electromechanics and mechatronics. Involvement of a mechatronics with the help of a simscape model. Simscape is a part of a simulink, but it is going to give it's going to give an environment for additional modeling of physical system, which may include some mechanical, electrical, hydraulics, and multi-body physics. So it's nothing but it's an environment. So it's going to give an environment to create a physical modelings. Okay. So what is that physical modelings? So I can see where I was done with all with the blocks. Is it or not? I have not seen the real circuits in the simulink. Okay. So Simscape helps me to see my real circuits. It helps me electrical. If resistance is there, in my circuit diagram, the resistance cannot be drawn here. I was given in the form of 1 by R. Is it or not? Okay. In the form of gain, I was given. I was not given in the resistance symbol. So if someone sees, electrical person sees that simulink, he cannot able to understand unless he was able to know the simulink model. What is the model is here? Why? Unless it was explained by the that technical expert, he cannot able to understand. The electrical engineer cannot able to understand, or the domain engineer cannot be understand the simulink model unless otherwise he going to explain to it. And second thing, it is going to give you some sort of graphical animations. So whenever after completing all the circuit, I'm going to show to you to the your boss or some person. I need to show in a graphical manner. So that cannot be done in my simulink, where only the blocks only will be available. So this simscape is going to provide a basic building blocks such as spring, motors, op-amp, current sensors, circuits, even a multi-body physics. Multi-body physics is a high level of physical environment where I'm going to show your, I'm going to show my, what is it, walls, op-amps, your drilling bits, everything, a physical model. A lift is there. I'm going to show you a lift, how it's going to work. I can able to simulate as a physical engine in my simscape. Okay, see, this is my electrical modeling, electrical dimension of a DC motor, whatever I discussed in the previous version. So same thing here. So same, but with some physical environment. So what is a physical here? Here, I added a inertia. Inertia is moment of inertia is there. Moment of inertia is there. I added in the mathematical model, but I added here as a physical model itself. Damper. Okay, damper is nothing, but here pulley is here. Is it or not? This pulley is rotated. It's called wheel and axle. Okay, whenever this is rotated, this object is coming down. Whenever I'm going to release it, it will drop it. Is it? So why I need to release it? There is no necessity of releasing. No, I can. If I was just to think of taking a water from the well, I cannot able to take a water at a stretch. Okay, what I'll do, I'll just use a rope to pull my bucket from the well for some height. Again, I'll give some rest and I'll give again a force. Is it or not? I cannot drag a complete force at one stage. I'll give a pass at in between because the force I required cannot be attained at a complete stage. So I need some pass. So that I'm going to say damper. Damper is going to be damp that frequency. There is a frequency is there. Is it or not? That frequency change will be reduced with the help of my damper. And I'm going to have a spring. A spring is going to be used to. So whenever I was pulling my bucket to the top right, so what is makes to pull it down? The gravity makes my bucket to pull it down. So in order to have a safety drop, what I'll have opposite force. So that is going to call a spring here. Okay. So your same example for your sewing machine is given here. So what is here? So just imagine a DC motor is attached with your needle. Okay. So whenever the DC motor is rotated, I'm going to convert with the help of a wheel and axle or a sperm gear, or I'm going to have a worm gear to convert my rotational movement into a linear motion. Okay, I'm going to convert the rotation. So what is here? I given a wheel and axle because for your convenience, given here wheel and axle is nothing but simply I'm going to say your car. Okay, my car is wheel is rotated, but my car is moving in a linear way. Is it or not? It is car is not rotating with the wheel. Wheel is rotated, car is moving in the linear translation movement, x-axis movement. Is it or not? So what is this? Rotational movement is converted into a translation movement. Like that, in your steaming machine, a DC motor is there. A shaft is coupled to a linear motion. So I can't have a needle is there. Whenever motor is rotated, what will happen? Needle will go up and down. Is it or not? So to go up and down, so I will have to move to down to get the up position. I'm going to use the DC motor to pull my needle to up. To drop down, I'm going to use a spring. Okay, the spring, whenever the force is to drop, the spring helps me to needle to drop down. So this going to give me the sieving action. Is it or not? The needle is going to go for a to and fro action in a faster manner. So to do this as a simlink, simscape will be doing it. Okay, so this is the model I'm going to do it. So unlike your simulink model, so I can't here there is a no gain and all. So directly I was adding a resistor. Is it or not? I'm adding a resistor inductor instead of my blocks as 1 by R or 1 by L. I was directly adding a here graphical structure of my your circuit diagram. Is it or not? So whatever you see here, the same was derived here. Is it or not? So this is called simscape blocked model. Okay, so in a simscape model, I will going to derive my complete setup. So I'll explain the components. What are those things? So the same thing model is derived as a final model. See, this is the DC voltage surface, resistor, inductor, and this is going to call it my motor. Okay, this is going to call as my motor shaft. Rotational electromechanical converter. That is, the electrical energy is converted into a mechanical energy. So I'm going to call it as a rotational electromechanical converter. Okay, so this going called as a motor. So this motor needed some housing. Okay, the motor cannot be, see, motor is there. I need some nut and bolt to tight the motor. So what is there? Vibration can be arrested. So it's a mechanical rotation. It's a housing. Nothing but a frame which is going to be given to my motor such that motor will be fixed to one point. Is it or not? Motor, if it is, I was not fixing my fan to the wall, it will be cannot be. It will be vibrate. Is it or not? So it is a mechanical rotational reference is the housing frame. Okay, and it is having an inertia. We already discussed about this moment of inertia. So moment of inertia is added to it. So this is C by R is nothing but my load. Okay, so this this is a load is added to my shaft converter. So whenever I am adding a load, I'm going to go for my things. So next I'm going to have a spring. This is a spring component. Load is nothing but spring. Whenever the component is coming back, the component should be returned back. So this spring is attached to it, and this is going to be measure the RPM of my motor. So I'm going to use a sensor called ideal rotational motion sensor, which is going to help to measure the RPM of my motor, how much speed I was rotating. That was measured using my rotation sensor. So I have two things. One is a angle and my RPM. So W is going to give the speed of my motor, angle, how much angle it is rotated. So that will be given with the help of my angle. Okay, so this is given. Okay, we'll discuss about this later again. So wheel and axle, again, what I said, wheel and axle. What is the role of wheel and axle? It is going to convert my rotational energy into linear energy, translation energy. So what is your motor rotation is converted with your needle, your needle to and fro action. Okay, that will be converted with the help of my wheel and axle. Okay, now you understood. After this wheel and axle, I will have the translation spring is attached to my things. Okay, so this it's called rotation spring and translation. So rotation spring, or I'm going to call it as a damper. Okay, I already said it's going to arrest my vibration. Okay, so whenever this is going to translation spring, normal spring. We have a normal spring. Is it or not? Normal spring is here. This damper circuit will be founded mostly in your bikes and all. Okay, bikes, cars and all. So arrest my vibration, I'll be having this damper. Okay, now ultimately I add a translation spring, and the spring should be attached to a mechanical reference. So it is a rotation reference and translation. So mechanical reference is attached to a surface. Okay. So and up to this you understood. And I'm going to measure the motion sensor. Okay, how much it is spring is moved. Okay, I'm going to measure. Okay, sorry, your piston rod is there. No, sorry, your needle. How the needle is moved? Is it or not? I'm going to measure the movement of my thing. Translation sensor. It is going to give again a output of my position and velocity. What is my position of my current needle, and what is the rate of speed of my your needle movement. So it should be equal to my motion sensor. Is it whatever my RPM? It should be equal to my the speed will be equal to my. But what is there? There is some other mechanical element is added in between. So there is a natural resistance will be offered. So there is a friction will be there. So that will reduce the your RPM and this movement velocity will be differs. Okay, up to this you over. And the basic components of this is so to see this is a simscape model. Okay, simscape model is different from the simulink model. So and now I need to communicate my simscape model with my simulink model. Okay, so yeah, this is you have already discussed in my simulink model. What is this scope? Is it or not? The scope is a simulink model which I need to communicate with a simscape model, which cannot be done. Okay, so simscape is a physical model. Simulink is a block model. Okay, so I cannot able to connect directly with a physical model with a block model. So I need a converter in between. Okay, this converter is a simscape to simulink converter. So this I going to connect with my scope. So if I want to communicate with my simulink param model, I need to use this simulink converters. Okay, so only whenever I was adding with all my scopes, I added with my simulink converter. And I added one more thing called solver configuration. Solver is so simscape is run on the base of some basic algorithms running. For this solver configuration is compulsory. Okay, so you have know the ODE45, ODE50. You have heard about Newton-Raphson method in your mathematics subject. If you have studied optimization and all, you would have heard about Newton-Raphson method and all. So that method is used here to run my simscape model. This is a part of a simscape. So whatever simscape model is done, I need to give this solver configuration on default. Okay, so I can able to change the ODE45 or ODE15 or some properties here. Okay, according to my requirement. On default, take it. Okay, don't change the property unless you are expert in that area. Okay, you understood the model. So can we go for the model? Can you able to see the model?
Yes.
Okay. So whatever I done with that, I will explain the diagram itself. So to open my simscape model, either I can do in a two-way. In my MATLAB command window, I can type SSC. Okay, simulink simscape new. Okay, SSC underscore new. Okay, I can type it and I can open the simscape model, or I can do in another way. Go for new in a blank model. Sorry. Here I can have a simscape model, is it or not? So I can directly select a simscape from here also. Either I can go by this way. In your MATLAB, I can type SSC underscore SSC underscore new. Okay, by typing this, I can create my simulink model. Okay, so this simscape model is created. So this is similar like my simulink model only, but it is comes with my default parameters, whatever I needed. Okay, for my simscape model, what I needed. So I'll add a few things and go for the model already drawn. Okay, so I already have a library browser. In the library browser, I don't think you can able to see my library browser. Okay, you can see my library browser. In the library browser, I have simscape. In the simscape, you can go for a foundation library. In the foundation library, I can have electrical. In this, electrical elements are there. Okay, rotational mechanical converters, translational mechanical converters, capacitors, inductors. Okay, are there? Is it or not? Resistors, everything is there. So I can able to take my electrical component out of this. So I'm going to have a DC supply. Is it or not? So I'm going to get a DC voltage source. Okay, DC voltage source is derived here. So I don't want this simulink to PS. I can delete this. Okay, can you able to see it? Okay, now I'll delete my simulink to PS converter. Now the voltage source is added here. So now after voltage source, what I needed? I need a resistor. Okay, after resistor, I need a inductor. Okay, the circuit diagram has a resistor, inductor, and then I can connect my okay, and I need a voltage reference. Okay, now after this, what I needed? A electromechanical converter. So type it up. Electro. Rotational electromechanical converter is added. So this will give the proportion later. Okay. Now I'll add my electrical part. So now this electrical part of the motor is connected, and now I need to connect with my mechanical part. Is it or not? So you cannot able to see the names. Is it or not? You can double click it in the top 3 dot is there. Is it or not?
Yes, sir.
You can see the 3 dot. In this, I can show the block name. So I can show the name of the component directly. Okay. So now the electrical side of my motor is completed. I will go for the mechanical part. So mechanical, what I needed to connect it. So I need to have a inertia. Is it or not? So mechanical needed. Okay. First, I need a mechanical references. And then I need a inertia. Amount of inertia is required. Okay, after adding moment of inertia to arrest my vibration, I need to add a damper. A damper should be added to the parallel to my mechanical system. So I'm going to rotate. Okay, now I can able to adjust my things. Okay, now I got my damper and my things. Okay, and after getting, I need to measure my speed of my thing. Okay, so to measure my speed, I'm going to have a sensor to measure my speed. Is it or not? So I'm going to have a rotational. So I'm going to add my R and R to it and C and C to it. Okay, so rotate. Okay, R and C is connected to each other. Get the side and flip top. Okay, now I got my rotation. So now I need to check the speed of my motor. Okay, how far the speed of my motor is done. So I'll check with my speed of my motor. I'm going to directly connect here. So speed of my motor is nothing but my RPM. Is it or not? So check. See here, go and double click my thing and check what is my output thing. RPM is my thing. Okay, now my thing. Okay, I need to connect. I already said to connect my thing. I need to connect my solver configuration. Okay. Now simulate the program. See, this is my output, which I got it in my mathematical modeling. Is it or not? You can see the simulate output graph.
Yes, sir.
Okay, this is
Yes, sir.
where we are discussed in my mathematical modeling. Is it or not? Where is my simulink? Same Z, it started from a 0 and it keep on increasing the speed like your fan. Okay, give us an example. This keep on increasing and after a certain period of time, it is going to attain my RPM, steady state. Okay. So far we have not added any load to my DC motor. So it is rotating in a free form. So when I was adding a load to it, your DC waveform will be changed. Okay, see here, can able to see it. So with the help of the same thing, I'm going to add all the things. So now I was giving the same rotation sensor. Now I converted into the wheel axle. So I was wheel axle is a here I going to have a ideal translation motion sensor. Okay, so here I going to simulate the your output. I'm going to check my output how it is going to be added to it. Okay, and now I'll come under the spring. Can you able to understand this diagram? After this rotational sensor, I'm adding to the your see, I'm adding to your wheel and axle, or otherwise I'll go to the diagram and I'll do it. Another 2 steps only. So you can see a wheel and axle. Now wheel and axle, what it shows? It is showing my A and P. So I should join my okay, action and pinion. Okay, can you see the window? The right window I'm showing. Okay, next what I needed. I need to add a spring. Add a spring. Sorry, this spring is a physical spring. Okay, now I'm going to add my translation spring to my. And after this, I'm going to add my mechanical reference. Okay, now I'm going to see through my output. So now I added my load to this. Is it or not? Now simulate my things. See, can you see the screen right now? After adding a thing, what is happening here? What is happening here? See, after adding my, this is the your sorry. Okay, after adding the spring, what is happening? So this is my speed of my motor. So what is happening? Speed of my motor is attaining to a just one. Okay. After your speed of my motor is rotated, what is happening? My spring is so what is happening? My piston is moving up. Is it or not? My your needle is here attached. Is it or not? My needle is attached. It is going to be moving up. What is there? The spring is going to act on the opposite side. So what is the speed is going to give a load to my needle. Is it or not? No, load to my needle. So what will happen to the load to the needle? When I was keep on increasing, the load will also going to keep on increases. So what will happen to my DC motor? The RPM is going to keep on reduces. Okay, at a one certain point of time, the DC motor will not. So keep on increases, RPM will be reduced. So I will change my spring constant so you can able to change. See, instead of 1000, I'm going to give 100. So now I'm going to simulate it. So you can see the difference in the scope. So initially we add my spring constant. See what is that? So now it is attained. Previously it is your maximum speed is attained by the 6, but now it is attained by the 15. And your see what is the thing? The frequency is less. Okay, so spring is there. The spring cannot able to oppose too much. So what is there? I can have a lot of frequency. There's a drag force is reduced. So I will be taking some more time. There I was done with the 6 seconds. Here I have attained my steady state at the 10th second. So whenever the spring constant is a decrease, the load is act on my RPM is also decrease. So DC motor will be able to do it off. If I'm going to remove the spring, what is going to happen? See, if I'm going to remove the spring, what is this? Can you able to see this graph? What is this? The piston is moving up and down. Is it or not? So this, sorry, this is my rotation angle. So this is my, okay, this is a position of my, sorry, you cannot able to see that. Okay, this is a position of my piston. If the spring is removed, what is happening? The spring extending, okay? Your piston is keep on extending. As my RPM is keep on going, your this thing is keep on extending to the extent, okay? So what is my rotation velocity of my thing? So I'll show in the graph or in a PPT. So okay, this is with the spring. Okay, with the spring, what is my rotation angle? It is going to be 0 to 200. And what is here? I already said, like my pulley, I cannot able to drag in a single stage. What is 0 to 200? Again, it is going to be reduced to 50. And again, it is given to, so what is here? Oscillation in my DC motor to attain the load. So whenever I was applying a load on it, what is my motor will oscillate to and fro. It was going to keep on oscillate and it is going to do. Okay, what is my speed of my DC motor? It is going to be get at 80 as the maximum at starting. Whenever load the spring is keep on adding, my speed is also reduced. This is a position of the needle which is similar like my your speed of my motor. So what is here? This start from 0. So it goes. So what is the position will not go in a negative. So what is happening? Your needle is increased to, that is, it is extended to 0.17 meter. That is 17 centimeter is extended, and again due to the spring action, it is coming back to a 5 centimeter. Again with the motor action, it is going back to the 12. With the spring action, it is coming. So this is a to and fro action is keep on doing. So this is your normal open loop condition. Okay, so this open loop makes me the at last I'll get my steady state to get my the condition. Okay, see about my speed and torque velocity also here. It is going to be similar to my change in the velocity of here. So whatever my output, it is going to be my RPM output. It is going to be here. But I already said you are not consider any resistance offered by the mechanical system. If we're going to add some mechanical, so will be added. So and now I removed the spring without spring. So without a spring, what is my rotation angle? It will go from 0 to 360 and again. So it is motor is rotating, is it or not? So whenever rotating, it go to 360, 0, 360, 0. It is motor is continuously rotating. So what is my speed? As I said, 0 to 420 it is going to attain after the steady state is attained. What is the position? It is linearly growing. So whenever the motor is keep on rotating, RPM is keep on there, your shift is keep on extending only. It will not retract back. When I am adding a spring only, it will come back to the original. So only I will have a to and fro motion in your sieving machines. Otherwise, what is the example here is, like a train, it will, whatever motor is given, like a train or a car, it will keep on push its motion in the front side if it does not have a spring. So the velocity of it is same like my RPM of my spring. You can understand the difference of my your with spring and without spring from the graph. Okay, so next so this is where my so same thing, only model using a simulink with a block. Here I was model using a physical parameters. Here I add one more thing in a simscape, what is called multi-body physics. So I can show you a direct spring structure itself, like animation I can able to show you. Okay, see here before going to the next topic, I'll show it. So the spring is here. So instead of showing a spring in a form of block, I'm going to show in a, see the spring, you can be able to see the spring. See, you can see the spring here. So what I do it, instead of adding this spring here, I going to add the piston to it. So whenever I compressing it, it can able to show the model here. But I need to add some. Okay, I cannot add directly here. I need to convert some damper force here. Can you able to see the difference of simscape multi-body physics? Multi-body physics is a direct animation, so such that I can able to go onto this. So you can see, so it's like a spring itself. So I can have a hydraulics valves. Sorry, I don't. See, this is a pulley. So again, I'm going to use a real-time elements going to be added in my things. So I can even simulate your robot configuration. So I can create a joints, multiple joints, and I can able to simulate my robot configuration using a multi-body physics.